Hello and welcome to Electronics Teardown. Today we will solve one task, and after solving that particular task, we will understand how we can convert an analog signal into a digital signal, and which will develop our understanding how the analog to digital conversion happens in all the electronic devices which we are using day to day basis. So let's understand what is the task. So the task is that we are having a street lamp. So let's say this is the street lamp. Again, my drawing is so bad, so poor. So we are having a street lamp. Now we need to turn this lamp on during night time, and we need to put it off during daytime. Okay. Now how this task used to happen as of now, there is a dedicated person who used to control this lamp and turn it on during the night time and put it off during the daytime. Now we have to automate this particular task. Okay, so how we can automate this task? I think the task is clear to everyone. We need to turn it on during night and turn it off during day. Now let's break down the task and try to find out the solution for this one. So if I'll break down this task, we have to do two major things. One is we need to identify day and night. See, for a human, it is very much easy to differentiate between day and night. We have different means of telling that. We will discuss that. Second thing is we need to control the lamp, obviously, automatically. So for that also, we have different solutions. If we talk about the solution for point number one, that we need to differentiate between day and night, humans have multiple methods for that. Okay, so let's talk about method number one for the problem number one. So method number one can be, if it is a shiny day, so and if it is a day, so there will be sunlight and there won't be any sunlight during the night time. So daytime there will be sunlight, night time there won't be any sunlight. Okay. Second method can be based on the time. Either world time clock or any time zone clock we can use, and based on time we can tell, okay, this is a daytime or this is a night time. Now this sunlight during days and no sunlight during night, we can correlate this with light intensity, because we are not going to use any human efforts to identify day and night or to distinguish between day and night. We need to build a circuit which will be capable of identifying whether it is a day or it is a night, and based on that it will do that particular action which is intended, that is turning on the lamp. Now this point number two is very much clear, that it will crisply give us the daytime and the night time, and we will be able to identify. Now, but if we use this point number one, the solution number one, where we are relying on the light intensity, then there are chances in few days we won't be receiving enough sunlight, right? and there are different parts of the world and in different countries where we receive less amount of sunlight compared to other countries. So this particular solution number one is not that much reliable. But if we will try to correlate this with our problem statement, that is like we need to turn on our street lamp when it is night and we need to turn it off when it is day. So generally, it is making sense when there is no light, when there is darkness on the road, we need to lit the road using the lamp. That is artificial illumination. And when there is enough natural light that is received from the sun, we should turn it off so that we can save the power. Right? So this makes sense logically. So instead of using solution number 2, which is even more reliable, we will use solution number 1 only. So that in case we end up turning on this particular light bulb even during daytime, that should not be a problem, because if the day is not receiving enough sunlight, we should lit the roads during daytime also, right? So as simple as that. So the solution which we will be using is this one. That means based on the light intensity, we will control the lamp. Now, what we need to do here in order to build that particular circuit or to build that particular sensor? So we need to have a certain sensor which can sense the light intensity, and based on that, which can generate a corresponding signal. So if you have watched the video part number 1, that is analog signals, so there we have built one circuit which is giving a analog signal based on the light intensity falling on that particular sensor. So we are going to do something similar. So let's draw the different blocks of this particular solution, and after that we will build the actual solution. So what we need to build this particular solution? We need a sensor which can sense light intensity. After that, this particular sensor will give us some analog signal. Okay, just try to plot the graph just to demonstrate. Then what we need to do, we need to analyze that particular signal and take decision. After that, we need to control lamp, that is our street light. Okay, so these are the parts. So as I already told, this particular sensor we have already built, so we will reuse that. Even I'll brief about this, what we are using to build this particular sensor. Coming to this analysis and decision part, what we need to do here? See, what will happen during the daytime if the sunlight is received in good amount? So how this light sensor will give us data? It will give us data something like this, like it will keep on increasing, and the light intensity will keep on increasing and the signal will also keep on increasing till the like noon time, or 2 3 hours after noon we used to receive good sunlight. After that, the light intensity starts decreasing. Okay, but up to certain point, the visibility will be there. So let's say like up to 5 o'clock or 6 o'clock or 7 o'clock, the light intensity is good enough. Let's say it is somewhere here. So up to this point, we are able to see and the visibility is good. But after this point, the visibility is low. So what we need to do is we need to put some reference point also. Are you getting? Like, this is the reference which we are putting on this graph. So if the light intensity is more than this particular reference, then we should turn it on, the lamp. And if the light intensity is below the reference, then, sorry, actually, if the light intensity is more, then we should keep the lamp off. And if the light intensity is low, then the reference which we set, and the reference we derived from the visibility, okay, then we should turn on the lamp. So what we have now, we are having a reference, okay. That reference we derived based on the visibility. Now, what type of signal we are getting from the sensor? We will get a electrical signal. So, if this we the signal which we have drawn, this is a electrical signal. This is a electrical signal. Either voltage or current domain. What is this voltage and current domain? I'll just tell, like, a signal which is changing the voltage based on the light intensity or changing the current based on the light intensity. Okay, in our case, our sensor will change the voltage based on the light intensity. So this reference also should be a voltage reference to this analyzer control block, which has to take the decision. So we have to fed some reference to this analyzer and decision making block. Means, this is our reference signal, this is the reference signal, we have to provide it, and this is the incoming signal. If the incoming signal is greater than the reference signal, then you have to send a control which is to make this lamp off. And if the reference signal is more than the input signal which is coming from this side, then you have to turn it on. Okay, so how we can build this particular block? You have heard about comparators, okay, or you can normally take an example of a operational amplifier also. So what a operational amplifier used to do, it used to take two inputs, input 1, input 2, okay, and used to compare these two inputs and generate output based on this. Okay, so this operational amplifier, or if I'll pronounce it more specifically, the comparators are the best fit for this particular block, because either of these two inputs, one input I can make as a reference input, and another input I can feed the data coming from the sensor. So this I can make sensor, and this I'll make reference, and based on that it will generate the output. Don't worry, we will be having demo, and we will be understanding each and every component and everything in detail. So now I'll talk about each of these blocks in detail. Anyway, we have covered this. This is the operational amplifier we are gonna use, but the circuit around it and everything we will understand. And the control block. So for the control block, what we can use is, we can use relays. So what relay used to do, it is a electromechanical switch. Okay, so instead of using a human to turn on the switch, let's say this is a switch. So instead of using a human being to turn this on and to turn this off, we can use the relay, which is a mechanical switch based on a input signal. Based on an input signal, it can If these are the two connections from the relay, it can connect them internally, short them internally, or it can open them internally based on the input signal. So it is a electromechanical switch. In a layman terms, automatic switch. Okay, where we no need to press it. Based on the input signal, it will automatically get pressed. As simple as that. So once the switch will be pressed, lamp will be turned on. So we have talked about the different blocks as an overview. Now we will create the circuit, how the circuit will look like for each and every block, and we will relate, and then we will go to the demo. So if we will talk about a sensor which can sense the light intensity, so we are gonna use LDR. Okay, this is called LDR, which is called as light dependent resistor. Okay, now how the circuit will look like, we are having this LDR, and then we will place one static resistor in series, and we will provide the VCC supply and ground. And from this point, the junction where LDR and the static resistor are connected, from this point we will get the output signal from the sensor. Okay, now what is the property of this LDR is, it used to change the resistance of this particular component used to change based on the intensity of light falling on it. So how the relationship between the light intensity and the resistance is, I is light intensity and the resistance is inversely proportional. So more the light intensity, less the resistance will be. Now let's take one situation where the light intensity is maximum, and to represent maximum we are just treating it as infinity. So if the light intensity is infinity, then the resistance will be minimum, least, and that least minimum we can, so I intensity is like 1 upon 0, so it is 1 upon resistance is minimum, theoretically 0, practically it won't be possible, but theoretically 0, like very negligible. So what will happen in this particular condition? So this is condition 1. In this condition, when the light intensity is maximum, and let's say we are not having this resistance here, and we just provided the VCC and the ground to this LDR. So what will happen in this particular situation? Two things will happen. One is, as the resistance is minimum, the entire current will travel from VCC to ground. It is a kind of, when the resistance is 0, we are shorting this circuit. So short circuit will happen. Okay, which is bad for the entire other components which will be connected to the same power supply, power rails. Okay, second thing is, this output signal, it will never change, it will always be 0 only. Why it will be 0? Because it is directly connected to ground, so the output signal will always be 0. So whether you will change the intensity or something, nothing will change, this output will always be 0. So two problems we identify, one is this short circuit, another one is this output doesn't make any sense to us. Now let's see, what if we connect a static resistance to this, and let's say this resistance is 10 kilo ohm. So what will happen in this condition 1 only, when this resistance is 0, the entire resistance of the circuit is 10 kilo ohm, is still 10 kilo ohm. So short circuit won't happen. So first thing is, we prevented the short circuit. Okay. So short circuit is prevented, and as the maximum current will flow through this LDR, and it is like behaving as a short up to here, so we will get the maximum output at the maximum intensity. So let's say we are getting, this is our 5 volts, so we are getting 5 volts. Now the intensity of the light is keep on decreasing. Now we are decreasing it, so the resistance will keep on increasing. So now the overall resistance of the circuit won't be 10k, it will be 10k plus some x value, and that x value can be 1 kilo ohm, 2 kilo ohm, or something like that. So if the overall resistance of the circuit will increase, then according to this, V is equals to IR. As V provided is constant, we are not changing that. Resistance is changing, based on which the current flowing through this particular circuit will change. Okay, so as the current through the circuit will change, the voltage at this point output will change. So the voltage will keep on decreasing, and it will be near to zero when the intensity is least, like fully covered, not exposed to light at all. So I hope you are able to understand this circuit and why we are using this static resistor here. It is to prevent the short circuit, and after adding this we are getting a valuable signal which is changing with respect to the light intensity falling on this LDR. Now in place of this LDR we can use photosensor also. So this photo sensor is also, it's like very much similar to solar panels. So as on the solar panel, the light intensity keeps increasing, the charge it is generating will keep on increasing. So the current through the circuit will keep on increasing, and the output signal will also keep on increasing. So we can use either of those. Either we can use the photo sensor or the LDR. The output of the circuit will be kind of similar. We will end up creating a sensor which will give a signal corresponding to light intensity. Now we have solved one problem, like we got a sensor which is giving us an electrical signal corresponding to the light intensity. Now moving to the second block. Second block is our comparators, which is like analysis and decision making, what to do, whether to turn on or turn off. So how these comparators used to work, those are operational amplifiers, and those are having a non-inverted and inverted input. Okay, so why this negative sign and this positive sign means this particular input, if let's say this is input 2 and input 1, so this particular input they will invert it and the output will be generated. So how the output will be generated? Output will always be equals to input 1 plus input 2. So as input 2 is inverted, so it will be finally input 1 plus inverted of input 2. So it is input 1 minus input 2. Now let's say we have given 2 volts at this input 2, and we are giving 3 volts at this input 1. So what our output will be? Output will be 3 minus 2, 1, as simple as that. Now if this is 1 volt, the input 1 is 1 volt and input 2 is 2 volt, so the output will be 1 minus 2 minus 1, means as simple as that. Here you can see the output is positive, here you can see the output is negative. Okay, Now, just one more addition, as I simplified most of the things while explaining this. So, just to give the right understanding, what it exactly do is, if the output is positive, it used to output the VCC. Means at output we will get the VCC. VCC means the maximum power which is applied to this operational amplifier, or you can tell comparator also. Okay, so generally we used to provide 5 volts VCC. So if the output, if the non-inverted input is greater than inverted input, we will get 5 volts as output. In practical, it won't be 5 volt, it will be somewhere around 3 volts. Okay, but that is called as high signal, or like 1, or like on. And when the output is negative, means non-inverted signal is lesser than inverted signal, then the output which we will get is will be 0 volt. So 0 volt means low, means 0, means off. Okay, now let's put sensor and this comparator together. We will be having one more challenge and we will solve that particular challenge also. But before that, let's put both of the things together. So this is our sensor. This is the output signal of the sensor, and we have placed a comparator here. This is non-inverting input, this is inverting input. At at this inverting input we have provided some reference signal. Okay, and this is the output. Now let's draw both the graphs. So the graph of this analog signal will looks like anything like so based on the light intensity we are getting a random value. Now how this operational amplifier graph will look like? For this one we need to have this reference signal. Till now we are not having this reference signal, so let's draw. And this is our light intensity, this is time. Okay, so let's draw this reference signal. So let's say this is our reference signal. So how the output of this operational amplifier will look like, comparator or operational amplifier? Here you can see the reference signal is greater than the signal coming from the sensor. So sensor is connected to non-inverting and reference is connected to inverting, means inverted, the negative signal is higher than the positive signal. So we will get the negative output. So negative output means we will get 0. So we will keep getting 0 up to this point. So up to this point, the output of this operational amplifier is 0. After that, what will happen? The non-inverting signal which is coming from the sensor increased from the reference signal. So the output will be positive and we will get the VCC. So VCC for sure will be greater than 0 volt. This is 0 volt. So it will be greater than 0 volt. Ideally it should be 5 volts whatever is applied to this, but practically we used to get little bit lesser than that. So let's say this is our VCC. So up to which we will be getting this, up to this point our output will be high, that is ideally talking 5 volts. After that, what will happen? Again, our sensor signal goes below the reference signal. So again, our output will go to low up to this point. Then again, our reference signal goes below than the actual signal of the sensor, and we will get high till the end. So this is low, we can tell this is high, which is 5 volt. This is again low, this is again high. So as you can see, this is the analog domain and this is the digital domain. You can see this signal is taking any random value and this is an analog signal. Just by putting a reference, we are able to convert this analog signal into digital signal. Why this signal is digital signal? It is having only two discrete levels, either 0 volt or 5 volt. Okay, so that is how using a operational amplifier, or more precisely a comparator, and providing a reference signal to that particular comparator, we end up converting a analog signal into digital signal. But there are lot of problems. Okay, we will discuss about these problems later on. Before that, we will do a demo. Whatever we learned or explained till now, we will check it practically how the things works. So we have our demo setup ready now. Here I have drawn the circuit which I am using on this breadboard. So we will go through one by one each component and explain what is there, everything. So this is the Arduino board. We are using it just to power supply, just to supply power to the circuit. So we are giving VCC and ground, that is 5 volts and ground to this circuit. Nothing else, no role of this Arduino apart from the power supply. Now on this breadboard, we are having this LM358 IC, which is a comparator IC. This is our photo sensor, which is sensing the light intensity. This is LED. We are just demonstrating this LED as a street lamp here, and this is a variable resistor. Now as you can see in this circuit, so you can see we are having this photodiode which is connected in reverse bias with the VCC and ground, and this is the 10 kilo ohm resistor, and from here we are getting our output signal. So this is the output signal which is corresponding to the light intensity falling on this photodiode. So this is the photodiode here. This is 10 kilo ohm resistance connected between VCC and ground in a reverse bias manner, and the point where photodiode and 10 kilo ohm resistance is connected, there we are getting our output signal. So this signal corresponds to the light intensity falling on this photodiode. So this is our analog signal which we are getting. Now this LM358 is a 8 pin IC, 1 2 3 4 5 6 7 8. So this is the IC here. So how this IC is configured inside, this pin number 4 and pin number 8, we have to provide ground and VCC 5 volt power supply to power on this particular chip. Inside this we are having two comparator ICs, as you can see. Means two comparator we have inside this. So one is this, another one is this. So this comparator, let's say this is comparator 1. So it is giving output at pin number 1. The inverted input is at pin number 2 and the non-inverted input as is at pin number 3. So the analog signal which we are getting from our photo sensor, we are putting it to the inverting signal. Okay, So because we need to flip the day and night scenario, so that is why we can give like either of these two. Either we can give it to the non-inverting or to the inverting one. It is just the output will flip. Instead of 1, it will start giving 0. Instead of 0, it will start giving 1. This pin number 3, we have connected the variable resistor here. Okay, so this variable resistor is to provide that particular reference signal which we were talking about. Okay, and to the output we have connected this LED lamp just to demonstrate this is the street light. So I think the circuit is clear to you now, and here I am having a multimeter on which we are reading the voltage which we are getting from the photo sensor. So as you can see is 0.013 volts we are getting from the photo sensor, which is fed to the non-inverting signal. And as you can see the LED is glowing, means the lamp is on, street lamp is on. Now what happens, now we will use a flashlight just to differentiate between day and night. Like when there is a day, this photo sensor will be exposed to more light. So just to mimic that particular scenario, I'll be using my mobile phone torch light for that. So as you can see, this LED is glowing, and I will expose this photo sensor now. So the photo sensor is exposed and the LED is off, and you can see the voltage which photo sensor is giving has been increased. It is now 0.108 something. I'll remove that exposure of light and the LED again starts glowing. I'll bring the exposure, so LED turned off. So means when there is more exposure to the photosensor, means which is correlating with the day scenario when there is a day. So during the day more exposure and the LED is off. When there is night, so less exposure to light and the LED is off. Day LED is off, night LED is on. So you can keep track on this voltage also. This is also changing corresponding to this. Okay, so what is happening, we have already like understood this particular thing. I'll just remove this just to draw the uh, graphs again. So this is the graph of the light sensor, the data which we are getting from the light sensor, and we have provided a reference signal. So this is the reference signal which we are providing from a variable resistor. This is to set the sensitivity. Okay, and like using this variable resistor, we can increase or decrease this reference point. Now, based on this reference point, what is happening? We are getting this particular output which is connected to this LED, and if there is more intensity, then the lamp is off. So now the signal is inverted because we need to, as I have provided this output of the photosensor to the inverting signal. So when there is less intensity of light, means less signal of the inverting, that time we want our lamp to glow. So as it is glowing, so up to this point it will be glowing, then the light intensity increase. So here in this region we need to keep it off, in this region we need to keep it on. So as the intensity increases, our lamp goes off, and it is off till intensity again changes. Okay, so this is the analog signal, this is the digital signal, two discrete levels. So here, by solving one task, we understood how we can convert an analog signal into digital signal. But as I mentioned previously, there's a lot of problem is still there in this analog to digital conversion. What is the problem? From this signal, we can just conclude two things. What we can conclude? Whether by like checking this state, if the state is high, now it has two states, high and low. Okay, so two states can give us two informations only two informations we can derive. Either if it is high means the signal which is coming from the photosensor is less than the reference, and if it is low means it is higher than the reference. But as you can see in this multimeter, the signal is 0.13, and then as the exposure increases it becomes 0.06897, 0.1, 0.2, 0.6. So there are so many values of this particular signal, but here in this digital domain, all these informations are lost somewhere. In this graph we have lot of information, but in this graph the entire information is lost. Only two information, whether it is higher than the reference or it is lower than the reference. That's it. So we did what we did. We converted a analog signal to a digital signal. That is done. This task is achieved. But along with that, we lost most of the information. So information is lost heavily. Okay, so one task is achieved, but information is lost heavily. Now in coming videos we will focus on this, why this information is lost and how we can convert an analog signal into digital signal without losing the information, or like without losing a heavy information, just a minimal loss of information will be there, so that we can recover the signal, or we can recover the majority of the information which is present in this signal. Okay, so please comment if you are having any doubt in the circuit, or you want a circuit diagram, or like anything. If you have any doubt, please comment in the comment section. And if you like the video, please give it a thumbs up. It will motivate me. And thank you so much.